Hello guys, this is other video of the group of the playlist general concepts of organic chemistry, which is on our channel Chemistry Crux. So fine, in this video we'll be discussing one more concept, that is electrophilic substitution reactions shown by benzene. We'll not be discussing the reactions itself, that is there are many reactions. There are sulfonation is there is nitration, there is halogenation, in which we'll be adding bromination particularly, or chlorination we do. So these all are substitution reactions, but let me say you, these are all electrophilic substitution reactions. That is, in them an electrophile is generated, and that substitutes the hydrogen atom in benzene ring, fine, forming the product that's particular to any reaction. For example, if we take nitration, in that nitration reaction, what we will get is we'll be getting this molecule, that is this and this, and NO2 will be replacing the H atom which was present in the original molecule of benzene. That's this thing, fine. Let me show it to you. So here H was present, now this H has been substituted by NO2. This time in nitration I took the example. If we took bromination, then this NO2 would be in place of NO2 we will be having Br2. If we took sulfonation, there should be SO3H. Fine, different examples we can take. There are many substitution reactions shown by benzene. Now all the mechanism of all those reactions follows three particular steps, and in this video we'll be discussing about those steps, so that we can get to know the substitution reaction mechanism. And when you go through this video, at the end of this video you will be able to deduce the mechanism for any electrophilic substitution reaction of benzene. For example, if I say you propose a reaction mechanism for sulfonation of benzene, fine, so you will be able to deduce a mechanism for sulfonation. You will be able to deduce this molecule, you will be able to work upon this reaction on your own, and you will be able to get this as the product, right? So what is that general principle, what is that general underlying mechanism we'll be dealing with in this video. So in order to get more videos like this, make sure to subscribe to the channel Chemistry Crux. Now let's start. Let me say you first of all, before I start the mechanism portion, let me say you there are few things about this benzene. This benzene, it's an aromatic compound, and it is highly stable compound. You must be knowing that. Now it is highly stable because of aromaticity, fine. So as a result of which, let me draw this line clear, like so. This benzene, it is highly stable molecule because of aromaticity. As a result of which, it doesn't undergo addition reactions. It doesn't show addition reactions. Why? Because if it shows addition reactions, in addition reactions what we see is that this bond, it will be broken down, and it has H already. Let me draw that with this color. This H is already present on this carbon, fine. So in addition reactions, what would happen is that a group will come, and that group will join here, will get added here, and this bond will be broken, and this group also will be added here, fine. So incoming groups will be adding like this. So what happens is that we have got something like this. Now if you see this molecule, first of all, it is anti-aromatic. It has 4 electrons. So it is highly unstable. Aromaticity has gone down for benzene, and also H is there. All right. Now you can see that this molecule, it is highly unstable. As a result of which, benzene doesn't show this reaction. Instead, benzene has, in fact, all aromatic compounds, they show something else. Some else behavior. Let me show you what they show, the behavior they show. What they tend to do is that they form something like this. they take a group. For example, here H is present, fine. So whenever a group comes in, let me draw this group with some other color, fine. Whenever a group comes in, benzene or aromatic compounds in general, they try to replace this hydrogen with this group, so that this aromaticity, this remains in place, it doesn't go down, fine. So as a result of which we get something like this. Let me show it in the same colors in order to make you completely understand what's going on, right? So a group is attached here. Now you can see this H has been substituted by this group, fine, and we have got compound in which aromaticity is still present, fine. So you can see this reaction is substitution reaction. Now substitution reaction, it can be either electrophilic substitution reaction, that is this group that was coming in, it can be an electrophile, then it is an electrophilic substitution reaction, or if this group coming in is a nucleophile, then this is a nucleophilic substitution reaction. Based on this incoming group, this can be classified as electrophilic substitution reaction or an nucleophilic substitution reaction. In this video particularly, we'll be discussing about electrophilic substitution reactions. We'll be taking up nucleophilic substitution reactions in some other video. Fine. So now let's see what happens in benzene. Let's take the mechanistic portion of this. So we have seen benzene or any aromatic compound, they only show substitution reactions instead of addition reactions in order to maintain aromaticity, in order to maintain their stable, structure. Now let's see the mechanistic portion for electrophilic substitution reaction of benzene in this video, right? Now, the electrophilic substitution reaction of benzene, it has 3 steps, fine? It has 3 steps. So whenever you take any other reaction as well, for example, I say you do the nitration of benzene, you will be knowing that nitration of benzene, it will be having 3 steps only. If I say take sulfonation of benzene or any aromatic reaction or any substitution, electrophilic substitution reaction of benzene, you will be saying there are 3 steps and you will be working up accordingly, right? While deducing the mechanism on your own. Now let's see what are the 3 steps. The first step is generation of electrophile. Generation of electrophile, right? This is something that depends upon this step. It depends on the reaction that we are taking, right? For example, if we take nitration of benzene, we will be using reagents like H2SO4 plus HNO3. This is called a nitrating mixture. HNO3, fine. Now this mixture will be taken while we saying nitration of benzene. If we take sulfonation of benzene, we'll be taking SO3 plus H2SO4. H2 is here, SO4, fine. Now this depends upon this step, it depends upon the reaction that we are undergoing. So in this reaction, what simply will be happening is that we'll be getting some electrophile as a result, fine. And that step you will have to work according to the reaction that you are going through, right? For example, if I take sulfonation of benzene, so in sulfonation I will be taking S, O, O and O. This is SO3, fine, plus H2SO4, H, O, S, O, O and H, fine. Now here is O. Now this O, it will be taking this lone pair to itself, this H coming in. So this H, it will be attacking this sulfur. Alright, this going here. So we'll be having something like this S positive, O3 and H. Fine. This H will be linked to this sulfur. So this will be the electrophile. Fine. In the same way, in nitration we can take NO2 is generated and positive O2. This will be, these electrophiles, they will be different for different reactions, and you will have to see them accordingly. You will have to generate them accordingly. Fine. Now this is the first step in the electrophilic, in the generation of electrophile. What we get is electrophile. From a material we get electrophile, and in addition to that we get some base which will be helping in the third step of the reaction, helping in the third step of the reaction. Now let's go to step number 2. Step number 2, in this step number 2, the formation of the Arenium ion takes place. Now this step is very crucial because in this step the electrophile attacks the benzene ring. For example, if we take the benzene ring here, what happens is that this bond, it's broken for some time. All right, here H is already present, here H is present. So this bond, it is broken down, and this electron from the bond is given to the incoming electrophile. As a result of which a bond is established between this carbon and electrophile. Fine, let me erase this line here and draw the arrow in order to show. So what will happen is this will be formed. Sorry, it was my bad. So here and here, positive charge is developed over here. Now H is present here and H is present here as well. Plus we have this electrophile got linked to this place. Now this electrophile can be anything. For example, if we take nitration of benzene, we will be saying it is NO2. If we take sulfonation of benzene, it will be SO negative, sorry, SO3H, right? This can be this. If we take bromination, it will be Br, it will be chlorination, it will be Cl. Fine, this will be different. Well, it will be different for different reactions that will be studying in the future, right? But in short, this ion is called the Arenium ion, and this is common for all the electrophilic substitution reactions. Now, why is it common? So now what happens in this is that you can see this Arenium ion, it is what we call as resonance stabilized. This goes here, positive charge comes up here. This goes here, positive charge comes up here. Then positive charge has developed here. Now reverse will be happening. A double bond will be formed here, which will be going here, and positive charge will be coming here again. Sorry, positive charge will be coming here again. Now this bond has been established. This will be coming here, and positive charge will be again developed here. So positive charge goes on here, this position, and this position. Fine. Now what happens is this is resonance stabilized, and it is an intermediate formed in all the reactions. It has been found that it is an intermediate. Intermediate means if the reaction, if we have this graph, this is, sorry, let me show it to you here. So this, if this is an intermediate, it will be on this, in this valley. If it would have been a transition state, then it would have been on this valley. Fine. For example, when this bond is being broken down, this state, it is a transition state, so it will be here. But this, it is an established intermediate, so it will be in this valley. Fine, in this valley of the graph of all right, just a moment. Yeah, it will be in this graph. So, and what is this graph? It is actually the energy graph, energy diagram, energy. All right, fine. So we take energy of these compounds, how it goes. For example, if it is benzene, sorry, if it is benzene over here, then this is this state where this bond is being broken down, and this electrophile, a bond with this electrophile, it is being established. This state is here. Once this state is established, then a positive charge on this location, it's Arenium ion, it is formed, and this is this state, which is represented by this molecule over here, it lies in this valley, means it's of very low energy as compared to this intermediate formed, and it has been established as an intermediate. Fine. Then some other reaction will be taking place, which would be another intermediate, and finally the product will be formed. Hope you understand these energy diagrams of different molecules, different reactions taking place. But this is not our focus. Our primary focus is that an Arenium ion is formed in the substitution, electrophilic substitution reaction of benzene. Right. Now the third step comes in. In the third step, what happens is restoration of aromaticity is, takes place. Restoration of aromaticity, right? This is what happens in the third step, right? Now let's see what happens. This is the Arenium ion that we have got from the second step. A positive charge, just a moment, a positive charge over here, H over here, and electrophile also linked to this state. Now what happens is, I told you in the first step that electrophile and a base is generated in the first step, that is in the generation of electrophile, right? This electrophile, it goes into the reaction, and this base, for example, in case of this sulfonation, this base will be this H O negative, sorry, let me write it down like this, O negative SO3H, this base. This will be base in case of sulfonation. In case of nitration, we will be having the same base actually, and nitration we have. All right, and other reactions will be having different bases. Now that base, it will be coming into play in the third step. That base, for example, let us take sulfonation into consideration or nitration. So this electrophile is either sulfonation. This electrophile represents as nitrate, or it represents as sulfate, SO3H. Fine. Now this can be either of two. Then this will be acting as that base which I was talking about, which is O negative SO3H. If nitration is taking place, then this will be the base. If sulfonation is taking place, then this will be the base. If any other electrophilic substitution reaction is taking place, then the base will be accordingly. I am saying that in these two reactions, the base is this one. Fine. So now what happens at this extract is this proton, and this electron pair is, it comes to this bond. So what happens is aromaticity is restored, and what we see is something like this happens. We have this electrophile here. Now you can see, just a moment, we have this electrophile here, and now you can see there is no hydrogen. This hydrogen, what appears is that this electrophile has replaced or substituted that hydrogen that was originally present here. So that's why it is called a substitution reaction, and electrophile has came in, so it's an electrophilic substitution reaction. So this is all about the, these are the three steps of electrophilic substitution reaction. The first one, that is, where is it? Just a moment. Yeah, the first one is generation of electrophile. We will be generating an electrophile, which will depend upon this electrophile generation. It will depend upon the reaction that we are studying. For example, if we take sulfonation, then we will be generating the electrophile accordingly, which will be, then used in the second step. Or if it is nitration, then we'll be, deducing the electrophile, accordingly. This reaction, this step, it simply depends upon the reaction that we are studying. The second step and the third step, they are universal for all the electrophilic substitution reactions. In the second step, Arenium ion is generated, which is an intermediate. If it is, from competitive exam point of view, you can say that this point is important, that Arenium ion that is generated, it's an intermediate and not a transition state. Means it is much more stable than a transition state, and its presence in the mixture has been established already by some experiments. So you should be knowing that this Arenium ion, it has a structure something like this, a positive charge over here, and electrophile got linked to this side and H to this side. Fine. So this is generated. After this step, the electrophile which was already present, the base that is generated in the first step, that is electrophile generation step, base is simultaneously generated in that step, which comes in and extracts this proton, as a result of which this electron is given back to this carbon, and again a double bond is restored here. So this is the final product that we have. Fine. Now let's take an example, or I think the video has gone too long. You can take the example of it. Let's now do the example as well. So if we take nitration of benzene, we'll be doing nitration, and in nitration what we do is that we'll be adding HNO3 in presence of H2SO4. It will be giving us something like this. Now anyone among you can generate the mechanism. NO2 is here. Now what happens? Let's take the first step. The first step is generation of electrophile. Here we are taking nitration, so we'll be generating electrophile from these materials, right? So it gives us something like this: H, O, N, O, and O is here with negative charge. This is nitric acid, fine. 1, 2, 3, 4, yeah, and a positive charge on this nitrogen, fine. Also there is H, O, S, O, 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 and H. This sulfuric acid. This will be taking this will be giving it to this. So what will be left with? An O2 positive plus S. This will be leaving as water, fine. I hope you understand that. These things will be studied in depth in some other video, but right now I'm trying to show you what actually the steps can be for sulfonation or for nitration of benzene. So we'll be having O negative from this, O negative, and SO3H, SO3H. This is the first step. So here is our electrophile, fine. Now the second step is formation of the Arenium ion. Let us do that. So here is benzene, here is benzene, fine. It has H over here. What will happen is that this electrophile N, O is here, fine, and a positive charge over here. This bond will be going here, and this will be simultaneously going here because N cannot form 5 bonds. So what we'll be having is something like this. Sorry. So you can now easily deduce any mechanism. Arenium ion is formed. You can see it is the second step of the reaction. H is here, and NO2 is here, NO2 is here, fine. Now what happens is that, all right, now NO2 is here. Now what happens is that the third step will come into play, in which a restoration of aromaticity will take place. Now we have got this Arenium ion, a positive charge over here. This has H, and it has NO2. We'll be taking the base that is formed over here. This will be O negative, SO3H. It will be taking this H positive, and this electron, it will be given to this carbon, which will form a double bond over between this carbon and this carbon again. So aromaticity will be restored. Now you can see we have 3 bonds again, and this H, there is no H present now, and it seems that this H has been replaced by this NO2. So substitution, and here you got the product. Now you can work yourself on sulfonation or bromination, or there are other electrophilic substitution reactions. We'll be taking also them one by one, but you can work upon all the reactions all the electrophilic substitution reactions that benzene can show. Only thing you have to work on is your knowledge base, that is this generation of electrophile. We will have to understand how different reagents generate electrophile while going through the reaction. Hope you understand this concept, and make sure to subscribe to channel Chemistry Crux and stay tuned for more upcoming videos. Thank you very much.